Welcome to the Deep Dive. We're here to cut through the noise and really get you the essential insights. Today, we're plunging into, well, a world that works quietly behind the scenes for almost every digital tool you use. Software testing. It's kind of the unsung hero, isn't it? Making sure the apps on your phone, the websites, even the big critical systems actually work and work well.
That's absolutely right. Software testing, it's not just about, squashing a few obvious bugs. It's really a deliberate, quite systematic approach to delivering software that's high quality, reliable. It's just foundational to meeting what users expect, building that trust, and honestly preventing those really costly disasters that can happen when digital things go wrong.
Definitely. And for this deep dive, our source material is this comprehensive software testing interview questions and answers guide. Now, I know interview guide might sound a bit dry, maybe just Q&A,
Yeah.
but it's actually a gold mine of the core knowledge. It gives you a real shortcut to understanding this whole field without drowning in jargon.
Absolutely. And our mission today really is to unpack these concepts. We want to distill the essential nuggets for you, so you get an understanding not just of what these terms mean, but really why they matter for the software you're using every single day.
Okay, so let's get into it. Let's unpack this and see what really stands out.
Great. Let's start right at the beginning then.
Yeah.
Foundational concepts. The actual building blocks of software quality. We've all heard software development, but what's the full plan, the blueprint for building reliable software? How does it make sure quality is built in from the start?
Right. So that complete blueprint, that's the software development lifecycle, or SDLC for short. Think of it like a really meticulous, systematic plan for creating software, step by step. It lays out everything from the initial idea, the planning, all the way through building it and then maintaining it afterwards. Its core purpose, making sure what gets built precisely meets what the customer expects, and importantly, stays within the agreed time and budget. Basically bringing structure to what could otherwise be, well, pretty chaotic. Okay, structure makes sense. And within that big SDLC structure, there are specific points where testing happens, right? Our source points out 4 distinct test levels. It sounds like quality checks are kind of layered in.
Yes, exactly. Layered is a good way to put it. These stages are critical for catching issues early, systematically. So first up is unit testing. You might also hear it called component testing or module testing. This is the most zoomed in level. You're testing individual units, tiny pieces of the software. Think like single Lego bricks. Testing them in isolation, making absolutely sure each little piece works perfectly on its own before you connect it to anything else.
Like checking each brick is flawless before building.
Precisely. Then, building on that, you have integration testing. So once those individual units, those bricks, are checked, you start combining them. This stage is all about making sure that when 2 or more pieces interact, they actually do it correctly, seamlessly. Do the Lego bricks actually connect properly?
Makes sense. Testing the connections. What's next?
Next, we zoom out further to system testing. Here, the entire computer system, with all its modules now integrated together, gets tested as a whole. This is where you verify the complete integrated product against those original requirements. You're looking at its functions, its internal structure. You're testing the whole Lego castle now.
The whole castle, okay.
Yeah.
And the final check.
The final stage, the ultimate check, is acceptance testing. This one's usually done by the actual end user or the client themselves. It's their final stamp of approval. They verify and accept the software system before it goes live, before it moves into the production environment. It's basically asking, okay, does this whole thing meet our real-world needs? Does it solve our problems?
Wow, that progression really shows the layers. Unit, integration, system acceptance. From tiny pieces to the user sign-off.
So, okay, we know when to test at these different levels, but how do you actually approach it? That brings us to these interesting colors of testing: black, white, and gray boxes. What do these tell us about how a tester looks at the software? Right, the colors. They basically define how much the tester knows about the inside of the software they're testing. So black box testing is like, well, you're given a black box, you can see what goes in, what comes out, but you have no idea what's happening inside. The tester has zero knowledge of the internal code structure, the paths, the implementation details. Their focus is purely external, based on requirements, specifications. Like, you push a button, you expect a certain result. You don't care how the button works internally, just that it does what it's supposed to.
Okay, so pure input-output focus. What about white box?
White box testing is the complete opposite. Think of it as a clear glass box. It's based on having full visibility. You can see the internal paths, the code structures, the actual source code itself. A white box tester is looking directly at the code, using techniques like statement coverage or decision coverage, we can maybe touch on those later, to make sure every line or every decision path in the code gets executed.
Total visibility. And gray box must be in the middle then.
Exactly. Gray box testing is, well, gray. It's a mix. Here, the tester has some knowledge. Maybe they have access to design documents or architectural diagrams, not the full code necessarily, but enough internal insight. This helps them create smarter, more targeted test cases than pure black box testing. They've got a bit more context. It's often a really pragmatic approach, giving you just enough info to be effective without getting totally bogged down in every single line of code.
It's fascinating how just the level of access changes the whole approach. Okay, so we've covered the big strategies, the levels, the perspectives. But how do testers actually, get their hands dirty? How do they hunt down those specific defects? What are some of the practical techniques they use to really dig deep?
Ah, right. Getting into the nitty-gritty. Well, one approach is random testing. You might also hear it called ad hoc testing. It's less structured. You're not following a strict script or specific requirements. Testers just kind of poke around, trying different things in different parts of the application, almost randomly, just to see if anything breaks. It can be surprisingly good for finding obvious flaws quickly, but it's definitely not systematic.
More like exploratory poking around. What about more structured ways?
On the more structured end, you've got things like data-driven testing. This is where you run the same test script over and over, but each time you feed it different input values. These values usually come from an external source, like a spreadsheet, an XML file, maybe a database. It's super efficient when you need to test the same function repeatedly with lots of different data. Think logins, forms, calculations. Ensures it's robust against various inputs.
Okay, using data to drive the tests. Now, you mentioned digging deeper into the code earlier with white box. What are techniques for that?
Yeah, so when you're really looking closely, boundary value analysis is a classic, powerful technique. It's based on the idea, which holds up surprisingly often, that errors tend to cluster at the edges, the boundaries, of valid input ranges. We call these ranges equivalence classes. So say a field accepts numbers between 1 and 100. A smart tester using BVA wouldn't just test like 50, they'd immediately check the boundaries. 0 invalid, 1 valid minimum, 100 valid maximum, and 101 invalid. Because history shows that's where developers often make mistakes, right at those edges.
Ah, so testing the transitions where valid becomes invalid, smart.
Exactly. It's about efficiency, too. And when you are looking directly at the code, white box testing again, statement coverage is a fundamental metric. It's pretty simple conceptually. You aim to make sure that every single executable line of code in the source is run at least once by your tests. Like making sure every instruction in a recipe gets followed at least once when you're test cooking it.
Cover every line. Got it.
Building on that, there's decision coverage. This goes a step further. It aims to ensure that every possible outcome of a decision point, typically an if statement, resulting in true or false, has been tested. So if your code says, if result 0, print positive, else print negative, you need one test case where the result is positive, testing the true path, and another where it's 0 or negative, testing the false path. You need to exercise both branches of that decision.
Okay, so testing both yes and no for every question in the code.
You got it. And the most thorough, often the most complex in this category, is path coverage. This aims to verify that all possible routes, all sequences of execution through a specific piece of code have been tested. As you can imagine, for anything more than trivial code, the number of possible paths can explode very quickly. So it's comprehensive, but often very difficult to achieve 100% path coverage.
That sounds incredibly detailed, almost like mapping every possible journey through the code. So beyond these core methods, random, data-driven, boundary, statement, decision, path, what about more specialized testing? Methods for unique situations or goals?
Oh yeah, there are loads, often tailored for specific quality attributes. Let's see. For performance, which is crucial for many apps, you have load testing. This is about pushing the application beyond its expected normal usage. You simulate many users accessing it at once to monitor how it behaves under heavy load, checking its peak performance, response times, stability, basically finding its breaking point.
Simulating rush hour traffic for a website, kind of.
Exactly. And related to that is soak testing. This is more about endurance. You run the system at a high, sustained load, but for a really long time it could be hours, even days. The goal here is to find problems that only show up over extended periods, like memory leaks or resource exhaustion, that slowly degrade performance until things crash. It's like a marathon, not a sprint.
Okay, load is peak stress, soak is long-term stress. What about security?
For security and finding robustness issues, fuzz testing, or fuzzing, is a big one. This involves throwing massive amounts of random, often invalid or malformed, data at the application's inputs. The aim is to provoke unexpected behavior, crash the system, or uncover hidden coding errors and security vulnerabilities that normal inputs wouldn't trigger.
Trying to break it with junk data. Clever. What about the user's perspective?
Right, user experience is key, so you have usability testing. This focuses entirely on how easy and intuitive the application is for an actual end user, someone often without technical or programming knowledge. Can they figure it out? Can they accomplish tasks efficiently? Is it frustrating or pleasant to use?
Testing how user-friendly it is. Makes sense.
And then there's end-to-end testing. This simulates a complete user scenario, a whole journey through the application. It tests the entire workflow from start to finish, making sure all the integrated components work together correctly and that data flows properly between them. Like testing the entire process of buying something online, from browsing to checkout to confirmation.
The whole user journey.
Yeah.
Okay. And what about keeping things working after changes are made?
Crucial point. That's where regression testing comes in. It's absolutely vital. Whenever code is changed, maybe a bug fix, maybe a new feature, you run regression tests. These retest existing functionalities to make sure the changes haven't accidentally broken something that used to work. It's about preventing backward steps or regressions.
So making sure fixing one thing didn't break another.
Precisely. And closely related is confirmation testing, sometimes just called retesting. It's very specific. After a bug has been reported and the developers say they fixed it in a new build, QA performs confirmation testing. They rerun the exact steps that previously caused the bug, just to confirm that the fix actually worked and the defect is truly gone.
Just checking the fix itself. Got it. That's a huge range of specialized tests.
It really is. And there are others too, like mutation testing, cross-browser testing, sanity testing, A/B testing, API testing, each with its own specific purpose.
Wow. Okay, so it's clear finding defects is a complex job with lots of tools. But once a defect is found, and you're right, it probably will be, it doesn't just vanish, right? There's a whole process. And you mentioned this is where it gets really interesting. The bug life cycle or defect life cycle. What does that journey look like?
Yeah, it's a structured journey. Every bug, once it's found, it doesn't just get logged and forgotten.
No.
It has a defined life cycle it needs to go through before it can finally be marked as closed. Now, the exact steps or statuses might vary a bit depending on the tracking tools. A team uses things like Jira or Quality Center, QC are common, and there's specific internal processes. But the core idea is consistent. A typical flow might be new assigned to a developer, open, developers working on it, fixed, pending retest, back to QA, retest, QA checks the fix, verified if fixed, closed, or maybe reopened if the fix didn't work.
So it's a workflow, tracking the bug from discovery to resolution.
Exactly. It ensures accountability and visibility. And a crucial part of kicking off that workflow is the defect report format. Clear communication is absolutely essential here. A good bug report needs specific details. Things like project or module name, a unique ID for the defect, maybe a short descriptive name, definitely steps to reproduce it, expected result versus actual result, maybe a screenshot or video, its severity, how bad is the impact, and priority, how soon should it be fixed, and violent details like browser, OS, and later who fixed it and when. This formal bug report is the key document. Without a clear, reproducible report, developers might struggle to even find the bug, let alone fix it.
Right, a bad report means the bug might just linger.
Okay, beyond just reporting, our source mentions some more nuanced concepts around defects, things like cascading, latent defects.
Yeah.
Yes, some interesting scenarios there. Defect cascading is a tricky one. This happens when fixing one defect, or even just the presence of one defect, actually triggers or reveals other previously hidden defects elsewhere in the application. It's like a domino effect. You fix the first domino, but it knocks over 3 others. It highlights how interconnected software components can be.
One bug leading to more bugs. Ouch. What are latent defects?
Latent defects are the sneaky ones. They're hidden flaws, undetected during normal testing. They lie dormant in the code and only surface much later, maybe even in production, when a very specific, perhaps rare set of conditions or user actions occurs. They're like little time bombs waiting for the right trigger.
Hidden problems. Sounds risky. What about classifying the bad ones? Critical bug.
Yeah, classifying is important for prioritization. A critical bug is severe. It means a major piece of functionality is completely broken or unusable. It might block testers from doing any further testing in that area, or it could have a significant negative impact on the customer's business if it reached production, like the checkout process completely failing on an e-commerce site that's critical.
Okay, major breakage
Hmm.
and a showstopper defect. Is that similar?
Very similar, often used interchangeably, but sometimes with a slight nuance. A showstopper defect literally stops the show. It completely prevents the user from proceeding with a task or using the application. The classic example is the login button just not working at all. You can't get past it, you can't use the app. The user is completely blocked. It might be critical, but the showstopper emphasizes that blockage.
Can't move forward. Got it. Now, what's the nightmare scenario for a testing team? Bug leakage.
Ah, yes. Bug leakage. That's the one that keeps testers up at night. It means a bug was missed by the entire QA process. It slipped through all the testing levels, all the regression checks, and was only found after release by an actual end user or customer in the live production environment. It essentially means a defect leaked out. It's embarrassing, potentially costly, and definitely something teams work hard to prevent.
A leak into the wild. Not good. And when you have a pile of bugs found before release, how do you decide which ones to fix first? Defect triage.
Exactly. You almost never have time to fix every single bug found before a release, so you need defect triage. This is typically a meeting involving key stakeholders, maybe the project manager, lead developer, lead tester, maybe product owner. They review the list of open bugs and prioritize them based on factors like severity, how bad is it, priority, how important is it to the business, risk, what's the chance it causes major issues, and maybe the estimated effort or time required to fix it. It's about making informed decisions to fix the most important bugs first, ensuring the biggest risks are addressed before launch.
So, managing the bug backlog strategically. It sounds like a constant battle against complexity. With all this effort going into finding and managing defects, how do teams actually measure how well they're doing? What are the key metrics for tracking software quality and testing effectiveness?
Measurement is absolutely key. You can't improve what you don't measure. There are quite a few important testing metrics. Some common ones include the total number of defects found, overall and by severity level, the number of defects fixed versus reported, the rate at which bugs are being fixed over time, is it speeding up or slowing down, maybe tracking bugs caused by new code versus existing code, regression. Also important is the number of outstanding bugs remaining just before release, and crucially, comparing the number of bugs found internally by the test team versus the number of failures reported by actual users after release. That comparison tells you a lot about test effectiveness.
That user-reported number sounds like the bug leakage metric again.
It's directly related, yes. Two specific ratios often mentioned are the defect rejects ratio and the defect leakage ratio. The defect rejects ratio looks at how many bugs reported by testers were ultimately rejected by developers. Maybe they weren't real bugs or duplicates or couldn't be reproduced. A high rejection rate might indicate issues with bug reporting quality. The defect leakage ratio, as we discussed, is focused on those bugs missed internally and found by users. It's often calculated as bugs found in production, bugs found internally plus bugs found in production. A lower percentage is obviously better here.
Okay, tracking rejects and leaks. What about measuring how good the fixing process is? DRE.
Right, defect removal efficiency, DRE. This metric focuses on how effectively the team finds and fixes defects before the software gets to the customer. It's typically calculated as number of defects found internally before release, total number of defects found, including those found by users after release. Let me rephrase that based on the source. Actually, the source example says, if 100 defects were found internally and 80 were fixed before release, the DRE is calculated differently there, as defects resolved, defects reported, 100. So 100 equals 80%. A higher DRE percentage indicates that your internal testing and fixing processes are catching and removing most defects before they ever reach the user. It's a key indicator of internal quality process maturity.
80% sounds pretty good. What about this intriguing term, the pesticide paradox? It sounds ominous.
It's a really interesting phenomenon and very relevant. The pesticide paradox in testing describes what happens when you keep running the exact same set of test cases over and over again. Eventually, those specific tests stop finding new defects. It's like the remaining bugs have become immune or resistant to those particular tests, just like insects can become resistant to pesticides used repeatedly. What it tells us is crucial. You can't just write tests once and run them forever. You have to regularly review, update, and add new test cases to keep finding new types of bugs. Your testing strategy needs to evolve along with the software.
So your tests can become ineffective over time if you don't change them up.
That's a great point. It shows testing itself needs continuous improvement. Okay, let's broaden the view again. We've talked techniques, defects, metrics. What about the overall infrastructure and planning that supports all this testing activity? Good question. Effective testing doesn't happen in a vacuum. Configuration management is fundamental. This is the whole process of establishing and maintaining consistency for all the product's assets, not just the code, but also requirements, documents, design specs, test cases, test scripts, even the testing environment itself. It ensures everyone is working with the correct, approved versions of everything, preventing chaos and errors caused by using outdated information. It brings efficiency and control.
Keeping everything organized and versioned. Makes sense. What's this workbench concept?
The workbench concept is described in the source as basically a structured way to define and manage a specific testing activity. Think of it as a template or a mini process for how a tester should perform a task. It breaks it down into 5 key steps. Input, getting what you need. Execute, running the test. Check, verifying the results. Production output, documenting findings. And rework, if needed, like refining the test. It provides a consistent structure for individual testing tasks.
A mini workflow for testers. And the test bed. Is that the actual environment?
Exactly. The test bed is the physical or virtual environment set up specifically for testing. It includes all the necessary hardware, software, network configurations, operating systems, browsers, databases like PHP, WordPress, PostgreSQL, MySQL mentioned in the source, everything needed to run the tests under controlled conditions that mimic the intended production environment as closely as possible.
The controlled environment for testing. And how is the overall approach planned? Test strategy.
Yes, the test strategy ties it all together at a high level. It's usually a formal document, often developed early on by a project manager or test lead. It outlines the overall approach, objectives, scope, resources, and schedule for testing the entire product. It answers questions like, what types of testing will we do? What tools will we use? What are the pass-fail criteria? How will we handle risks? It's derived from the business requirements and sets the direction for all testing efforts. It's the master plan for quality assurance.
The big picture plan. Okay, now there's a distinction you hear a lot in quality assurance that can be confusing. Verification versus validation. They sound similar, but the source emphasizes they're different. Can you clarify that?
Yes, this is a really important distinction to grasp. They address 2 different aspects of quality. Verification is primarily about checking if you're building the product right. Does it meet the specifications? Does it conform to the design documents and standards? It's often done using static analysis techniques, meaning you're reviewing things without actually running the code. Think code reviews, inspections, walkthroughs of requirements or designs. You're checking the blueprints and the construction process.
Building it right, according to the plan. Okay, so what's validation?
Validation, on the other hand, is about checking if you're building the right product. Does the software actually meet the user's real needs and solve their intended problem? Does it fulfill the business objectives? Validation is typically done using dynamic analysis, meaning you are executing the code. All the functional testing, usability testing, acceptance testing we talked about falls under validation. So verification checks against the specs, validation checks against the actual user needs. You need both for a truly successful product. Are we building the product right? Verification. Are we building the right product?
Validation.
That clarifies it nicely. Verification, right process. Validation, right outcome for the user.
Okay, shifting gears slightly to something huge in modern development, automation. You hear about it constantly. When is automated testing the way to go compared to good old manual testing? And what are the key tools?
Right, automation is a massive topic. It's definitely preferred in critical scenarios. Think about tests that need to be run over and over again, like regression tests after every code change. Humans get bored and make mistakes doing repetitive tasks. Computers excel at it. It's also essential for performance testing and load testing, where you need to simulate hundreds or thousands of users impossible manually. Other good candidates are tests that take a long time to run manually, tests that need precise timing or data input, or situations with very frequent software deployments where you need fast feedback.
So speed, repetition, scale are key drivers for automation.
Exactly. But it's not a silver bullet. Manual testing still has its place, especially for exploratory testing, usability testing, ad hoc testing, things that require human intuition, judgment, and exploring unexpected paths. Automation is great for verifying known conditions. Manual testing is often better at discovering unknown issues.
A balanced approach is needed then. What about specific tools? Selenium comes up a lot.
Selenium is definitely one of the dominant players, especially for automating web browser interactions. It's an open source framework with bindings for many programming languages. The source mentions comparing it to SQL, which is different. SQLi uses image recognition to automate GUIs, so it can work on desktop apps or things Selenium can't easily handle, like Flash objects, though it has its own complexities. Selenium is primarily web-focused.
Okay, Selenium for web apps. What can it do?
A lot. Selenium WebDriver lets you write scripts to control a browser, navigate to pages, click buttons, fill forms, check text. You can easily take screenshots with it, which is super helpful for documenting failures in your automated test reports. And for scaling up, there's Selenium Grid. This allows you to distribute your test execution across multiple machines, operating systems, and browsers simultaneously. You can run your test suite much faster by parallelizing it. It's huge for saving time in CI/CD pipelines.
Running tests everywhere at once. Powerful. What about TestNG?
TestNG is often used alongside Selenium, particularly in the Java world. It's an advanced testing framework that provides more structure and features than basic JUnit, for example. It helps organize tests into suites, manage dependencies between tests, run tests in parallel, generate better reports, and it has good mechanisms for handling exceptions during test runs. The source also mentions a handy feature. You can easily disable or skip a specific test method just by adding an annotation like @test, enabled false, useful when a feature is temporarily broken or not ready.
So Selenium drives the browser, TestNG helps manage and run the tests. Got it. We're covering a lot of ground. Just a couple more key terms from the source material to help round out our picture of this testing world.
Sure. One really important document is the Requirement Traceability Matrix, or RTM. This is essentially a table or spreadsheet that maps each requirement from the business requirements document to the specific test cases designed to verify it. It's crucial for ensuring that every requirement has corresponding test coverage and helps track the testing status for each requirement throughout the project. It provides that end-to-end traceability.
Making sure nothing gets missed.
Right.
And you touched on this earlier, but just to reinforce, SDLC versus STLC.
Right, worth clarifying again. SDLC, Software Development Lifecycle, is the entire process of creating software planning, design, coding, testing, deployment, maintenance. It's the whole lifecycle. STLC, Software Testing Lifecycle, is a subset of the SDLC. It focuses specifically on the testing activities within that larger process: test planning, test design, test execution, defect reporting, test closure. So, SDLC lives within the SDLC. SDLC's goal is working software. SDLC's goal is tested, quality assured software.
Testing is a dedicated cycle within the main development cycle.
Okay.
And one last interesting one, bug bounty.
Ugh. Bug bounty programs. These have become quite popular. It's basically where a company invites external security researchers, ethical hackers, or even just skilled individuals to find and report vulnerabilities or bugs in their software, often their websites or apps. If someone finds a valid security issue and reports it responsibly, following the program's rules, the company pays them a reward, a bounty. It's a way for companies to leverage a wider pool of talent to find security flaws before malicious actors do. It's crowdsourced security testing, essentially.
Paying people to hack you ethically. Interesting approach. Well, this has been an incredible deep dive. We've gone from the absolute fundamentals, the SDLC, the testing levels, through all those different techniques: black box, white box, fuzzing, regression, then managing defects, measuring quality, and finally the tools and strategies like automation and traceability. It really paints a picture of just how much meticulous effort and structured thinking goes into making sure the software we use every single day actually functions reliably.
It really does. And if we connect this back, understanding these processes, even at this level, I think it empowers you, the listener. You're not just a passive user anymore. You have a bit more appreciation for what's going on under the hood. It highlights, how much deliberate thought and specialized skill is involved in making technology dependable. Even seemingly simple apps can be incredibly complex behind the scenes, and testing is what makes them usable.
Absolutely. It gives you a new lens to look through. So here's a final thought to leave you with. Knowing what you do now, even just from this discussion about the sheer intricacy of software testing, what's one specific thing you might look for, or maybe appreciate differently, the next time you fire up a new app or use a piece of software? Maybe you'll think about those boundary conditions when you enter data, or the silent work of regression tests, keeping things stable, update after update. Something to ponder. We definitely encourage you to continue your own deep dive into this really fascinating world of software development and quality.
Academy Podcast, where ideas ignite and futures fall.